So let's continue with our mathematical derivation of the fast inverse square root algorithm. We've seen in the previous video that we can relate our decimal number x with the integer representation of the floating point number ix through this equation here. So ix is equal to log to the base 2 of x, which has been scaled by this factor L, and we've added on the factor L times b. So we've got a scaling and a shifting. Now we can rewrite this in terms of the log to the base 2 of x. So log to the base 2 of x is equal to ix upon L minus b. So we've just transposed this equation to get this equation here. Now why bother doing this? Well, here is the secret to the fast inverse square root algorithm. If we were to look at this y is equal to 1 upon root of x, we can rewrite that as y squared is equal to 1 upon x. We can take the log of both sides of it, so we'll have log to the base 2 of y squared equals log to the base 2 of 1 upon x. So by the rules of logarithms we can take the 2 out, so we get 2 log to the base y. X to 1 upon x is the same as x to the minus 1. So again we can take the minus out, and this gives us the minus log to the base x. So we can then take the 2 down here, so this will give us log to the base 2 of y is equal to minus 1 upon 2 log to the base 2 of x. So this is just another way of writing this equation here. And you can see how useful it is, because we have got a method of generating this log to the base 2 of x, albeit an approximate method, and it's given by this value here, ix upon L minus b. So we can therefore replace each of these logarithmic terms with the terms here. So the log to the base 2 of y can simply be written as iy upon L minus b. We have our minus a half, and our log to the base 2 of x can be written by as ix upon L minus b. So we have this here. Now if we transpose this for the actual value of our y, we'll get this equation. So you can check that out for yourself. I've just taken the b across here, and I've taken the L up. And we can rewrite it in this terms here. And finally we can simplify it so that iy is equal to 3 upon 2 L times b minus ix upon 2. So this is the final point that we're going to get to. This equation here relates our values of our ix and our iy, which in effect is just this equation here, y is equal to 1 upon the root of x. So we've rewritten this inverse square root in this form here. So we can generate this really easily, because we've only got a few operations. One, we've got this here, which is a single number. It's 3 divided by 2 times the value of L times the value of b. So in our 32-bit floating point number system, the L is 2 to the 23, and the value for b is the bias, which is 127. So in our 32-bit floating point number system, this is 3 upon 2 times 2 to the 23 times 127. And this thing here is nothing other than the magic number that people tend to talk about whenever they're talking about this fast inverse square root algorithm. So the beauty about this here now is that rather than having this esoteric magic number, we actually have a mathematical derivation which tells us exactly where it came from. And I would suggest to you that the mathematical derivation is far more magic than the idea of having some magic number. Now, the last part is we're going to subtract off this ix upon 2. But we can generate the ix upon 2 very simply, digitally, by shifting. We simply shift to the right. And when we shift to the right, it's a division by 2. So we've got a shift and we've got a subtraction from a number. So it's a really, really fantastic and easy way of generating an approximation to the 1 upon the square root of x. In the next video, we will finish off with the actual algorithm and we will look at the magic number, and we'll see how the magic number that actually gets used compares to the magic number that we have here. And we will also generate the magic number for our 16-bit floating point number. One thing I'll leave you with just before we go is that in effect what we've generated here is a class of algorithms. So these algorithms, if you like, they could be called shift and add algorithms. So we have a simple shift here. Now in this instance here, it's obviously a subtraction, but you're just adding on a negative. So it's still the same thing. It's a shift and an add function. And we can generate lots of different mathematical functions. We don't need to generate just y is equal to 1 upon root x. We could go through this same process here and we could generate another approximation to another function. So as I said, this is part of a class of algorithms called shift and add. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.